Paul, but and a PhD in robotics in 1983 from Institut National Polytechnique, and an habilitation HDR in 1996 from Paul Sabatier University. He contributed and took important responsibilities in several national, European, and international research for collaborative projects. He is a well-known figure in the robotics circles. His main research contribution falls in the field of robot decisional and control architectures, but also in the area of task and motion planning, and in the area of multi-robot cooperation and human-robot interaction. Dr. Alami is holding the academic chair on cognitive and interactive robotics at the Artificial and Natural Intelligence Toulouse Institute. So we are very happy to have Dr. Alami here today, and he's going to be talking about decisional issues for human-robot joint action. Over to you, Dr. Alami.
Now I have some. Thank you very much. Thank you for the introduction. I'm very happy to be here and to share with you this discussion and this presentation. So please, could you warn me 5 minutes before the end so that I conclude, because I'm a little verbose and perhaps I will not stop on time, but I will do my best, of course.
Okay, no problem.
Okay. So as you mentioned, I have my students have made yesterday a tutorial about some of the tools and approaches, essentially the tools based on the approaches I will discuss here. So perhaps it should have been better if I've done this presentation before, but however, these are complementary I would say approaches to the problem. So I will focus here essentially on the, I would say, broad spectrum of this challenges for human-robot interaction, and more precisely human-robot joint action, as it is mentioned here, and even more precisely on the challenges for the decisions of the robot, challenges for the robot. So I have, yeah, sorry. What is the challenge of the cognitive and interactive robot? It is essentially to devise and build and also deploy the cognitive and interactive abilities that will allow the robot not only to achieve its collaborative task with the human, but to achieve it in a way that it is pertinent, of course, also transparent, legible in its intentions and behaviors, and also acceptable by its human partner. And of course, one can imagine that the applications or applicative domains of such robot will be the service and assistant robot from one side, but also the teammate robot in the factory or in the field. And it is important to understand also that somehow the interactive challenge of AI is fully realized in this human-robot collaboration, and I will try to, I would say, to illustrate and argue on these aspects. It is indeed very challenging to build systems where humans and robots can and have to decide and act together, share the decision, share the space, and share the task. So, well, this is somehow we need to do it. It's not a choice, because when we look broadly to the future robots, essentially there are applications where we can understand that these robots will replace humans. A number of applications concerns not the replacement of humans completely, but the use of robots to assist, serve, or collaborate with humans. And other kinds of applications are essentially rehabilitation and augmentation. But this means that the presence of the human in robot action is something that is needed, that is mandatory. It is more and more necessary for the robot. Because of course we are moving. I have some difficulty to change my slide, sorry. Hello, do you hear me?
Yeah, we can hear you, Professor Alam.
Very good. I'm in difficulty. It seems that my screen is blocked. Sorry, one second. Yeah, I will do it this way. Is it? Yeah, it seems that my my keyboard is blocked. I will unshare and share again. Sorry. Yeah, I don't know what happens. Is that it seems that my my keyboard is blocked. I'm really sorry for that. How? It's a pity because this doesn't allow me to change my slides. So sorry, I will. Huh. Yeah, I think it's my PowerPoint. I will quit it and launch it again. Sorry.
Yeah, sure.
Yeah. It happens only when you are online, you know, these kind of things.
Murphy's Law, right? So.
It happens only when you have no choice. Okay, so I will continue discussing during this and this, and I think what is important is the challenge, as we have seen here. Let me see. Yeah, now it seems that my things are coming better. Yes, I am. I was here. Yes, very good. So I'm sorry again for this issues. So what is, so as I mentioned clearly, the robot and the human will have to be together, and so it is a challenge for the robot, not for the human, of course. And what is difficult for robot autonomy already? We know this, and we know that autonomous robots is very difficult, essentially because when it has to face variety of environments, variety of tasks, uncertainty before deployment, you don't know exactly what will happen before deploying, and uncertainty in open, non-protected, and non-structured and dynamic environment, which is exactly what happens when you are in human-centered situations. Acting in presence or in synergy with humans is a real challenge for the robot. And this is, as I mentioned, because of these main issues of complementary challenges to the robot, besides its needs to perform the task. These issues of safety and verifiability, pertinence, and explainability of its behavior. And somehow, we are moving from the dream of the autonomous robot to the challenge of the collaborative robot. And I am in a generation where our dream and challenge was that the robot was alone, like this one, and it was very capable, it was very intelligent, and you give it a task or goal, it performs the task, and it's finished. Okay? It does a job and it's finished. Okay. Sometimes it is ready for a new adventure, or perhaps it is finished in it when doing its task, etc. It was this kind of system, the lonely hero. Okay. The robot was performing alone its task. But now we are moving to something different. More difficult, which is in this area of inquiry where we have to understand, to implement, and to deploy the social side of the robot. And my discussion will be essentially about what does it mean, okay? And what are the consequences of this new ability, this new needs somehow on the decisional abilities of the robot. I argue that for doing this, we need a robot that is more intelligent than the robot that is alone performing its task. And sometimes we need also more subtlety from the designer's side. I will not discuss about this level of HRI, which is the sensory motor level. Now we have these robots, they exist, and they are able to comply with humans do not consider the human perceive. Okay, here this a very known video from our colleagues Sami Adadin from DLR, who has done this work during his PhD thesis. And what I can say about this is that, well, he's still able to answer simple questions, since now he's professor at TUM, a very famous professor. So the safety somehow of this robot is already there. Okay, these robots are caused when there is no other solution, low injury risk, and are adaptive. But they do not consider this force control level and this adaptive level, like the one from Sapienza in the other side, is essentially avoiding obstacle and adapting to a dynamic obstacle and reducing the force of the consequence of collision. Our approach here is to endow this kind of robots now with the decisional abilities. And this means essentially that I will switch this because I do not have time, essentially to take into account the social needs of the robots and how to integrate it essentially in this notion of human-robot joint action. And when discussing about joint action, in fact, there is a community of philosophers and psychologists who are specifically studying this notion of joint action between humans. What make us, we humans, able to collaborate, able to perform collaborative action with our peers? Okay, we are able to do this because there are a number of, I would say, signals, a number of behaviors, a number of principles that we apply when we are performing a joint action with our colleagues and or peers. And for example, we are it is easy for us to detect if a person is a good partner, a good teammate or not, how it works with us when performing a task. So for those who are interested, we are organizing a series of workshops with psychologists and philosophers. Already 11 workshops have been organized. The last one was in robot philosophy in 2020, and we are planning to organize others. And for those who are interested, they are open and you are invited to join. And I'm giving here the link where you can find a number of presentations and slides and papers that summarize this discussion between philosophers, psychologists, and roboticists around this question of human-robot joint action. Indeed, this concept and the mechanisms of joint action are key. Okay, it is essentially the ability, the social interactions that we use when two or more individuals coordinate their actions in space and time to bring about a change in the environment. Okay. How are we able to do this? We are very good in doing this, and there are a number of examples where we are able to work and collaborate with humans. And what is key here is that, of course, things can go awry very easily. And it is there that our ability to perform joint action of humans and to adapt and to monitor and to facilitate the action of the other is key when we perform joint action with humans. And it is exactly on these topics that we'll try to, I would say, to develop the behaviors of our robot, okay, for this kind of applications that are now very known somehow, okay? Service, assistance, and teammate or co-robot, like some people say. So now we are on the topic building the decisional processes of the robot. So this is a slide which tries to summarize a little how we tackle this issue. You have the human, you have the robot. They are facing one another. They are somehow in multimodal dialogue. They can do gesture and actions and speak. They are also doing mutual observation. The robot observes the human observes the robot. And what is very important is to endow the robot with the capacity to consider and to take into account the fact that it is observed. Okay? It is the second level which is important. And having this, we assume there is a task to perform. And the question here is that it's a task which concerns the human and the robot, and we want it to be performed in the best possible way, which means it should be efficient, but also safe. And also, as I mentioned, the behavior of the robot should be acceptable and legible by the human. And in order to do this, we endow the robot with decisional or plan-based, we call it also online deliberation capabilities, because it is important for the robot to be able to reason about what is happening, to anticipate what the human will do and what they will do together, and also even to be able to be proactive in its behavior. And one thing which will be very important, and this comes from the fact that the robot considers that it is observed by the human, is this notion of theory of mind, equipping the robot with a limited ability, but still present, of predicting and reasoning about not only human activity, but also human mental state. Okay, does he know what I'm doing, what I'm waiting for him or her, do we share a common knowledge about what is happening? And this is key in order for the robot to adapt and to perform correctly. So, and I will give here some examples in the how much time? Yeah, in 12 minutes that I still have. It is a constructive approach, essentially. I will show some examples of systems that we have implemented from the two aspects. One, which is very important, which is the situation assessment and interpretation, behaviors and abilities of the robot. Okay. And the second aspect, which is the synthesis of robot behavior. In fact, what we have done based on this constructive approach is that we have studied, based on this discussion with our colleagues, as I mentioned, of philosophers and psychologists, of some number of key ingredients that we think are necessary for the robot to behave like we want. And these key ingredients are components that are implemented in software modules that are integrated and articulated in the control architecture. Some of them are mentioned here. For example, one key aspect is already human-aware navigation. Okay, how the robot should simply navigate, or human-aware, the ability of the robot to move its arm and to manipulate interactively objects with humans. And these are based on something that is key, which is this notion of managing the beliefs of the human, what the human knows about the task, what the human knows about the robot, and the task which is performed. And in order to do this, we are also working on the key notions of affordances, which allow the robot to focus on what is important, what the human can do, what the human can see, what the human can reach, and the same for itself. And this will allow the robot to build what we call a perspective taking, to place itself in the shoes of the human. Okay? And having this, only then, the robot will be able to plan, okay? And to build a plan, to build a shared plan, where it will help the human, assist the human in performing the task. And another key aspect here is that even if it seems like a multi-agent system, human and robot, they are not equal, okay? The robot is here to help and to serve the human and not the converse. The human is not there to help the robot or to facilitate the work of the robot. We want exactly the converse, of course. However, the human should be and must be, as we have seen, a good and partner of the robot. Because if he is not, or he or she is not, this cannot work somehow. We have applied this, and we have some results on various contexts. I'm giving here some examples. We have deployed, for example, a service guide robot in Schiphol Airport. This robot was able to guide persons from one gate to another in the terminal of Schiphol Airport, and it worked quite well, avoiding in a comfortable and legible way the crowd, I would say, in a crowded environment, and also guiding correctly a person to a specific gate and a request. We have worked also on the assistant robot at home, where essentially the issue here is to perform, I would say, intelligently fetch and carry tasks. Okay, give me this. Where are my glasses? Where's the remote control of the TV, etc. Where I would like a book, and the robot is able to do the fetch and carry and give the object in a comfortable way and adaptive way to the human it assists. We have also developed an application where a robot is here in a mall and giving indication to humans. And here what is interesting, it has, and again illustrating this ability of doing perspective, the robot for doing this guidance, not only reasons of its own perspective, what it sees, but also on the perspective of the human. Okay, and eventually asking the human to move a little in order to better see the shop, for example, or the corridor or the stairs the robots wants to point at. The last example that I'm showing here, which has also allowed us to exhibit some of the capabilities of a robot, is I would say the teammate robot in a factory. This was done in a project where we illustrated the ability of the robot to perform and assist and share an assembly task with the human. Here again, we're doing fetch and carry, but also adapting to human needs and to human change of mind or change of focus during action, during the accomplishment of the task. So under the hood, it's I would say it's more complex. Of course, it's essentially a number of components, of software components that and what is important in these components, which correspond to the architecture, is this notion that has been illustrated yesterday by my students of the consideration of humans in the models that are used in these different situational assessment or planning algorithms. What has to ask itself permanently is what to do at any moment. This is not always clear. Who should act, human or robot? Sometimes it is better, it is preferable that the robot does nothing and allow and leave the human do, okay? Because the human has chosen to do, or it's preferred for him. Where to perform a task is quite a complex question, and we have some answers on it. It's not easy when the robot has chosen a task to perform. It's not easy for it to choose where to perform it. When is very important, and we can understand this quite easily. And another key aspect is how. Very often, there are different ways, there are many ways to achieve a task, to perform a task, and only some of them, the how, are preferred to others or are pertinent compared to others. And these questions has to be considered by the robot at different levels of abstraction, from the highest level to the fine details of the actions, and also at various time of horizons. What should I do now? What are we planning to do in the future? And all this means that we are in the quest of models, of the pertinent models, and also the quest not only of models but also of I would say validating these models. And since I have 5 minutes now, I will switch to some examples. The first one, as I mentioned, is perspective taking. Okay. The perspective taking is the ability for the robot to compute affordances and to put itself in the shoes of the human. Here, a situation that we would like to avoid, okay, having the different perspective. The robot should comply and adapt to the perspective. As consequence, a big consequence on situation assessment globally, because it means that the robot should not only build its own belief of the context, but also the beliefs of the human. And I will give an example of this, and I think it will be almost the end of my talk before the conclusion. How are we doing this? We are doing this essentially by equipping the robot with the ability to build through special reasoning the perspective of the human. So not only it builds its current state of the world, but it estimates the state of the world like it is seen by its partner. And we have taken as challenge as a psychological test very known by psychology, which is called the Sally and Ann test, which is essentially, which is used to see if children are able to understand that different beliefs of the same situation can happen in the situation. I will summarize it here very quickly. We have Sally and we have Anne, and the child is looking at this scene. Okay, Sally has a basket and Anne has a box. Now Sally has a marble and she put the marble in the basket and takes the marble and puts it in the basket. And then Sally comes back and you ask the child who have seen the scene, the child, where will Sally look for her marble? And what is interesting is that the small children until the age of 2 or 3, even more sometimes, for them there is only one truth. They will say, oh, of course Sally will look at it in the box, which is of course wrong. They are not able to understand that there are different perspectives because there are different histories. And we have tried to implement this on a robot where we have 2 humans and the robot as an observer, and see it now running. So what you see here is the robot tracking and building a situation assessment of what is happening in front of it. So we have 2 humans, green coming. So now the robot, using simply here very simple perception, is building, updating its world state, and also estimating the world state from the perspective of another guy called green. The second guy, but also try to compute the positions of the objects. And what will happen now, and the robot is tracking it, while green is away, blue modifies and it is observed the situation. You see, it takes the object there and put it in a place that is not now visible to blue. Okay. Here the robot again updates the state of the world, and he has also updated the state of the mental state of blue. Green comes back. You will see it coming back. This is running real time. Okay? And now the robot is able to compute the new affordances, and essentially the fact that green has observed that the object was no more on the table, okay, and he doesn't know where it is, okay, since it is hidden to him. And this can allow the robot, for example, and this is what's happening in this plan, to, if needed, to build a plan which it has first to inform the human about where the object is before performing a collaborative task with him. And having this ability will allow the robot to be far more pertinent in its abilities. And we have seen some examples yesterday from my students on how this can apply in planning, in reference generation, in controlling the high-level task of the robot. Okay. Here again, the same. The robot is not only building its own perspective, which is the left one, but the perspective of the human. So, for example, here the robot is able to understand, because he has seen the human, that he is seen by the human. Here are other situations where the robot is able to compute the visibility and reach of the human. And having this, the robot is able, for example, to put an object in a place where his partner can see it and reach it with less effort. Since I'm almost out of time, I will switch to the conclusion. Move to the conclusion directly. And mentioning that, of course, this work is not my work only, but the work of a large number of co-authors with me, and there are also a number of co-chairs with me in my chair of cognitive and interactive robotics. And the key issue that we are studying in this framework are cost-based search linked to proxemics, visibility, effort, and social rules, constraints on placement and postures of robots, grasp, reach, also protocols that should be respected, and rhythm and social rules that should be respected by the robot. And finally, the features I mentioned, which are comfort, acceptability, and intentionality. And some of them can be somehow introduced in the models, at least in the first step. Thank you very much. I'm stopping here and open for questions.
Thank you, Dr. Alami. I think that was a really fascinating and interesting talk. And I think, I guess this is certainly the future aspects and future topics where all of us have to think about the kind of things you mentioned when we design robots. If there are any questions, you can type them or maybe unmute yourself and ask. And while that is happening, I had a question on the 4 experiments you showed. And there were 2 of them where the service robot was basically answering questions, whether in the airport, Schiphol, or in the mall. And the question to you is, do you think the physical aspect of the robot, its ability to give gestures, is really important in these applications? I mean, does it make a difference, or just having like a console with a LCD screen and a microphone is good enough, right?
It's a good question. I think that there are. It depends on the. It depends, I would say, in the task and the context. In some tasks, in some contexts, what is needed is embodiment. Okay, the robot should be present to share the task and the space. Okay, for example, to point to something, we have to share the perspective. On a screen, you cannot share the perspective. Perhaps you can show the place where to go. Yeah, of course, there are ways of doing, but really sharing the perspective, for example, or handing over an object, etc., you need the presence. Now, does the robot need to be like a human or like a humanoid? That's not for sure, not necessarily. It needs certainly a way to point, to physically point. It needs also some kind of head for focusing and the interaction, and also for exhibiting its attention. Okay, so this is what we think is trying to be important. And you are perfectly right. What we are trying to do, and this is what we are doing with our colleagues, is to do some kind of minimally, I would say, minimally presence of physical robot, but still pertinent and necessary for the task.
Great, thank you. I think that was a really wonderful talk. And again, I thank you, and also your students for giving the tutorial, which is, as you said, quite complimentary to what you said.
Thank you very much.
Yeah, and I think since we are running a little bit behind time, a few minutes, maybe we'll request the people, if they have questions, to perhaps directly reach out to you, maybe send a mail or something.
In chat, yeah, chat or mail, that we would.
Yeah, great.
Thank you.
So,
sorry for that.
yeah, okay, thank you. No, I think that's good. Yeah, so we'll move on to the next speaker. It's my pleasure and privilege to introduce the next speaker, Professor Leena Vachani. She's a professor at the Systems and Control Engineering Group at Indian Institute of Technology, Bombay. She has contributed in the areas of embedded control and robotic applications on topics like multi-agent mapping, exploration, patrolling, coverage. She has developed laboratories on embedded control concepts, autonomous robots, multi-agent systems, etc. And she's also the faculty advisor of AUV IIT Bombay team since its inception in 2010. She works in the areas currently in perception modeling for single and multi-agent systems, edge computing with IoT and so on. She also is the project director for this new technology innovation hub at IIT Bombay under this National Mission on Interdisciplinary Cyber Physical Systems. So with that very brief introduction, I will hand over the podium to Professor Leena Vachani.
Thank you so much, Professor Amrita. And thanks, Professor Rachit, for wonderful insight into your work. All right, so let me first start with sharing my screen. And I will request your inputs on the same.
Yes, we can see it and it's full screen now. Yes, and we can.
Thank you so much. Thank you so much. All right. So this work is about the swarm aggregation without inter-agent communication. And I picked up this particular topic because we approached this particular problem in a slightly different manner than what is existing. And it is conveying from the need of the application. And so instead of covering different problems that we are addressing, I am going to focus on this particular problem only and how we approached it. All right. So Professor Amrita has already given a brief on it. So it's just that I'm working with SysCon as of now. Before that, I did my PhD from IIT Madras. Mostly I work in the areas of motion planning. And recently I have started looking into the robotic applications in IoT and IoT frameworks. All right. So I have structured this particular talk to explain you a little more about the swarm aggregation and what we picked up from the nature. Looking from the application needs coming from embedded control systems and what was my approach and the results and summarize. Let's see what we pick up from our nature, right? So, of course, we have seen this flock of birds many a times. This is particularly a video from Northern Europe where millions of birds do appear in a season, and then it has been interpreted that these flock of birds, it's very important to notice what could be the objective behind this flocking behavior. So in this particular one, they look forward for combined decision on finding a shelter. This is what is really amazing to look at. All right, let's look at the next video. This is the ants, and let's see what they are doing here. They are making some kind of a bridge to move from one place to another, where, of course, if only one ant would have been doing it, would not be possible. Ants are a wonderful example of teamwork, and that's what is coming up from this video. All right, let's see what comes up from the School of Fishes. See here that when the food is served, food is basically given to the fishes, how fishes attack to the food here. And that's what inspired us to mimic it in some sense. Of course, not completely, because it's not easy to interpret what the nature is bringing to us. So what we interpreted out of it is that when a food is dropped, most likely these fishes are not communicating to each other, right? So what will it help us in doing that? Of course, they are doing some collective task and so on. But let's see if this particular task of grouping these agents, in all these three applications, we saw that they are looking forward for achieving a common goal, right? Which perhaps is not possible with single agent. And that's what is important here. In case of fishes, if they always be in a group. And why are they specifically these small fishes? Why are they in groups? Because otherwise the predator will come in and harm them very clearly, very, very easily, right? So that's what is the nature is some way bringing us to us. So if we look at the scientific perspective to the swarm aggregation problem, where we are grouping the agents to perform a common goal. Of course, from the scientific perspective, it's really nice to look into these behaviors, model them, and look at whether what kind of collective behaviors they are giving. They facilitate easy collection of data or information from some places. And of course, they are basically a good interactive and the mission control kind of behaviors or the models that we can create applicable to multiple use cases and so on. And when we look from this particular swarm aggregation from the application perspective, of course, we can look forward for, as I said, the motivation is like what single agent is not able to do it, but a group is able to do it, is something we can look forward for implementing in our robots as well. So what nature tells us, okay, teamwork is one of them. At the same time, from the robotics domain, it can come out as collective decision making for localization. For example, certain robots are giving one kind of perspective, whereas the other kind of robots are giving different perspective depending upon their field of view. And when the information is collected, and of course the collected information will give better interpretations. And that's where the group of agents would be doing some kind of a collective behavior with the help of collecting information from multiple sources. They will be helpful in safe navigation because they are capable of giving different perspectives and so on and so forth. As I mentioned, they can be used for data collection and information exchange. And there is many more one can look forward from exploring, learning from nature, what they are doing it and whatnot. Okay. So if we see from what is already existing, right? So there are methods existing which are purely control based, and they look into the model agent dynamics, they look into the global local knowledge of other agents. So what is important here with when we are dealing with group of agents? It is important not only to look into whether they are collectively doing the task, but whether the teammates or the agents within this particular group is capable of understanding each other. So what is the knowledge being exchanged between them about their own state? And of course, the control-based methods talk about the stability guarantees in some way. Whereas when we look into bio-inspired methods, they are more or less the algorithmic methods, started with the bees behavior and so on. So they work onto the finite state machines to model interactions. Many times they talk about there's no communication between the agents because it's not clear from nature whether they communicate to each other. Birds do, fishes do at times, and it had and the literature do says that because there is some kind of sounds that they have captured in literature, saying that if they had started doing some kind of an activity, they capture a different kind of a sound. So perhaps they are communicating to each other using those sound or some other signals and so on. But these algorithmic ways do lack giving the lack giving the stability guarantees. So in this case, so what we look into is when we studied this particular literature and understood what is available in the literature. So we started asking this question that if we have to solve this aggregation problem without any agent communication, and with, of course, when agent communication is not there, then whatever individual agent is able to sense with that information itself, are we able to reach to a fixed target? So our common goal is to reach to a given target. Then we said that, fine, algorithmically, maybe I'll be able to do it, but can I give this particular guarantee when specifically there is no inter-agent communication? So then what is the dynamic part here? What is going to change is the agent information between them, which is being integrated by individual agent individually. All right, so we formulated an objective here saying that, okay, there's no inter-agent communication. But at the same time, usually in these form aggregation problems, agent is a small size. It means the processing capabilities are very limited. And we are trying to solve this problem with onboard sensing itself. So we need to, and at the same time, we are trying to give the stability guarantees. It means I should be able to design a controller which is going to be using the embedded platform, because I want to solve this problem with the onboard capability itself. All right, so our need is very nice, saying that, okay, I want to design an embedded controller for an agent now, singular agent. So let's understand this particular problem from the embedded control system and what are the challenges involved. So when we start looking into the embedded platforms, which are mounted on individual as onboard sensing, processing problem, and so on, actuators, and so on. So we model it as kind of a control system where the system is our robot or agent, and whichever way. Okay. So this particular problem, we considered modeling the robot as a unicycle model, and that follows later. But let's see from what are when we start looking from the embedded perspective, what are the advantages and what the limitations to come. Okay, so what are the advantages? Of course, when we solve this problem using embedded platforms, it gives smaller semiconductor area, low power consumptions, good for small sized robots. That's what we are looking forward. Of course, many times it's cheaper, cost effective options, and so on. And since we have to look forward for many such agents in our problem, it's going to be easier in bulk production. But what are the challenges? The challenges are when we have to interface with sensors and actuators, because my processor is small, I should have that much interfacing capability, what kind of sensing I'm looking for, what kind of actuators I'm going to, and how many such actuators I'm going to interface with this embedded board. Since this is digital world, I will have to talk about quantization. I should be worried about quantization, sampling time, and digital computation, which may not be a problem when I'm solving this problem or implementing the controller in a computing machine like laptop or some better computing machine, something like that. But when we solve this problem from the embedded platform, we have to really think about, when I'm doing these digital computations, whether this much data bit, it is 8-bit is just sufficient for doing the computing, or I should be considering this particular problem to be solved with 16-bit processor and so on. Anyways, we'll not go into those details, but of course, the bottom line is when we design a controller, it requires a special effort to be designed. Okay, so let me quickly brush through what all embedded processors are available in market, what are their disadvantages and advantages, so that we will have idea about what kind of challenge we have to face. So these categories are microprocessors, microcontrollers, FPGAs, DSP, embedded Linux and platforms, and so on. Of course, when we design a controller or when we start working with an agent, we have to always give this answer when to use which embedded platform. Mainly because we want to use it as a controller and interfacing it with sensors and actuators. So when we see from the general purpose microprocessor, of course, this we choose it based on 8-bit, 16-bit, or 32-bit kind of requirements, and we can always relate it to the computing machines that we have. Sorry. All right. So, okay, I was here at the microprocessors. The advantages, we already have the high-level languages to work with. Many softwares are available with us, but at the same time, it takes up the unnecessary extras of semiconductor space, which may not be, cannot be customized at all. When we look from the microcontroller perspective, this is very nice. Microcontroller is good for interfacing with the sensors and actuators to a certain extent, right? So when we have few sensors and actuators to communicate with, microcontrollers is a good answer to give. And small level of programming is fine. Certain topologizers are already available because it also has the RAM and ROM, some data collection facilities also there. So this becomes typically a good choice for the controller design. Its name is itself says microcontrollers. All right. So, but at the same time, when we select this, we have to select the microcontroller based on the available memory, what peripherals, what IO ports we have to look forward, and so on and so forth. When we see from FPGA perspective, the FPGA's architecture is such that you will be able to program each of these lookup tables and so on and so forth. It has hundreds and sometimes thousands of IO pins surrounding its pins and so on, surrounding its outer periphery and so on. And those many pins are available to us. So when the sensors, which are taking many pins to be connected with, to many, say 10, 20 such actuators to be interfaced, FPGA is making a wonderful choice for us. It also provides the facility for the parallel processing. So multiple sensors, when it is connected with, each of these sensors are independently being serviced, processed, and then given to the controller, and so on. So wonderful choice when one has to look forward for parallel processing, reconfigurable hardware, and this becomes the first level of design for system on chip designs. So one can look forward for designing in FPGA and then taking it to the ASIC levels and so on, design their own chips and so on. So this is also looking forward for solutions. This also gives solutions for real-time applications. As I mentioned, one may not be looking forward for multi-core facility and so on, but a customized solution, which is like, okay, I am having these many sensors, these many actuators, these types of sensors, these types of actuators. I will look into programming it in hardware, those drivers only, which are to be interfaced and so on. And so it is very useful when the IO requirement is high. Similarly, we have DSPs. DSPs typically, of course, designed for signal processing, but it's now being used for the controller applications as well. When we have the sensors, and the sensor processing is requiring a lot of signal processing capabilities, which are given as a feedback to the controller. This makes a wonderful choice and becomes an add-on for the controller. This is nowadays very popular, where we look forward for embedded Linux kind of solutions, where we have common Linux kernel and so on, and the libraries which are application dependent. Again, you can customize these libraries, which is required by you, you as in required by the applications, what sensors, what kind of actuators we have, just load only those drivers and so on. ROS also has similar, robot operating system also has a similar concept, but embedded Linux is much more elementary, and one can look forward for customizing it. Of course, the interfacing becomes easier and the real-time applications. When we studied these particular processors available, embedded processors available in the market, what is more important for us to know what are the computing bottlenecks, because we are going to design a controller specifically with certain challenges, certain objectives that we have selected. So what we have to see is that when we have to look into implementing this controller, whether we have fixed point operations or floating point operations available, we know that there is a limited hardware available, limited memory, limited processing available to us, limited power capabilities, of course, because the processing depends upon the power requirements then in some way, relatively. And of course, if it is digital computations, then are we able to make the computations only with the shift and add type of computations? Very challenging problem, because the control computations, the maths functions that come up in the control law is something we should be able to handle it in the digital world itself. All right. So with this, we set up another objective, design this controller for the swarm aggregation with no communication, no inter-agent communication, based on algorithm or the control laws that require limited computing and onboard resources, because we know that its implementation is to be on a smaller device. All right. So let's see what was our approach. I'll not go into the mathematical details of it, but giving a superficial idea about how we approach the problem. So let's see from both the ends, from the application perspective, we set an objective of no inter-agent communication. By the way, this objective also gives a secured kind of environment, secured kind of solution for the swarm aggregation, because there is no inter-agent communication. There's no communication from the control unit to this. Each of the agent is working independently. They are taking their decisions on their own, not communicating to each other. So there's no requirement of secure communication at all. So that's what is the major advantage, and it's being explored in the development part now. Of course, as we spelled out from the embedded point of view, the design is, the controller design should be such that it requires limited computing and limited onboard sensing. All right, let's see, when we frame the problem, we frame the problem saying that, okay, I have the field of view available with sensor, which is sensing the presence of this and at the same time presence of the agent, the nearby agent. So for example, I'm talking about the ith agent, which is on the left top bottom, if you're not able to see my cursor. And these gray circles are other agents, jth agent and the kth agent. And in this particular diagram, ith agent is able to view jth agent, but not the kth agent. So how do we formulate this problem? By saying that, okay, I have this particular distance available with respect to the agent, and its angle with respect to its current forward direction, which is delta aj in this case. So I have a field of view, which may not be the entire 360-degree or whatnot. Of course, this particular problem is solved in 2D. I just brought the 2D problem to be discussed here. Its 3D counterpart is also ready. This is going to help us in understanding a little more. That's the reason I'm solving this. I'm just presenting in the 2D form as of now. All right, so now let's see how we approach the problem. We approach the problem by saying that, okay, I have a sensor view available. What happens if the other agent is in the view or other agent is not, no agent is in the view, right? So let's categorize them like that. So category is based on free subsystem. So each of the agent is a subsystem, and it's free if it is there's no other agent around, and it's an engaged subsystem if there's one more agent in the field of view. All right. So then we decide upon this particular criteria. Is this control law is also it's more important to understand from the perspective of embedded domain that when we talk about this kind of a control law, which is kappa I, which is just a simple constant, and the control law, and the feedback is of course this theta I dot, which is only the signum function. So when it is signum function, you can see related to your digital computing problem, your signum function is only just a comparator, whether the sign is positive, negative, or of course, if you are dealing with zero as well. So your decision is only based on the sign of this feedback, right? So what is happening in this case is this particular control law is making the agent to go towards the target. I'm not bringing out how this is derived and whatnot. It's giving you an information that this particular control law for the ith agent is making sure that it is moving the robot or the agent towards its target, which is the origin here. Whereas in the engaged subsystem, what we have is nothing but the control law. This is, by the way, the steering control law, depends upon the signum of this theta I dot. At the same time, this particular angle, which is making which is nothing but the angle with respect to the agent which is in the field of view. So the idea here is to bring out these maths is to tell you that these control laws which are developed are computationally inexpensive. They are based on the comparators, decisions to be taken, when to switch from free system to free subsystem to engaged subsystem, and so on. At the same time, this control law development is actually motivated by the attractive and the repulsive fields of potential fields, where it is nothing when there's no this particular term kappa I sinum theta I is making sure that it's attracting. It's an attractive kind of a function which is making the agent to move towards the target, whereas this particular term ki signum of delta ij is more like a repulsive function, and it is avoiding the collision with respect to the nearest agent. So just by understanding that the control law is a combination of this attractive and repulsive functions, and this is what the individual agent is doing, is the swarm aggregation problem solved, right? So this is what we tried to address it. We made sure that while designing this control law, we made sure that the attractive function is always bigger than the repulsive function. So somewhere you're always moving towards the target, at the same time making sure that you are avoiding the collision with the nearest agent and so on. All right, so we said that let's talk about stability now, stability of this particular swarm aggregation problem. Of course, since we are changing the decision, whether from free the control law is changed from when it was in free kind of decision making, when there was no agent nearby, and then to the engage control law when there was at least one agent in the nearby. So there is a switching is happening. So what we have to give the stability guarantees in this case is that individual subsystem is stable, first of all. All right, so we took, since this is nonlinear control law applied to a nonlinear system, we took help of the nonlinear methods to say, okay, this individual subsystems are being stable, right? All right, but there is a switching happening. So when there is a switching happening, is it still being stable? Because you are moving from one system to another, switching from one system to subsystem to another subsystem. So there's one more concept we'll have to say, that when it is switching, it is still stable. So we took help of these multiple Lyapunov functions. The one Lyapunov function talks about the free subsystem stability. The second Lyapunov function talks about the engaged subsystem. And the switch system talks about whether these multiple Lyapunov functions are still having some kind of commonality, so that we can claim on the stability. right? So I'm not going into those details, but giving some kind of an overview of how we tackle this particular problem. All right, so here are some results now. Okay, so this particular is your goal point. So what is happening here now? You can see that these green color dots are green color agents are the ones which are free agents, whereas these red color ones are the engaged ones. Engaged ones, as in at least there is one agent which is in their vicinity. So they have come closer to the target. At the same time, those which are away from the target, they are still struggling to reach to this, right? To this particular target. And you can see that these green color ones are still moving. Sometimes red turns into green and green turns into red in order to do that. All right. Now, when we have already defined the stability and we have the guarantees with the stability, we said, okay, let's explore. Let's explore what is possible now. So we perturbed the system, perturbed few of these agents. Since we knew that it is a stable system, we knew that this is going to end up into giving the swarm aggregation. Even when we have the perturbations, we have moved certain agents away from what they had already achieved. We explored this particular problem with the static obstacles in the environment. So there are pathways which are maybe blocked. We did not change any control law, by the way, right? So since there's a local sensing available, we said, okay, when local sensing is available, then it doesn't matter if the nearest, whatever obstacles is coming in the view is static or the other agent or whatnot. We're not making any difference out of it. So let's see if this works with the static obstacles cases also. So it automatically makes a pathway to reach to this particular target. Single control law applied to each of these particular agents independently, they are able to do it. Similarly, if there is a pathway available, and by the way, this particular application is again motivated by how fish feeding is done to catch these fishes, right? So that's where they make a nice pathways and the fishes they move towards their feed available, and they get trapped at the place where the food is served. All right, so that's all from the results side. Of course, we had some experimental results as well, which I'm just trying to skip due to the limitation of time. All right, so we compared this particular result when the communication is available or when we have local interactions between the agents. And we saw that our method was at par with those methods as well. So then the question is whether this inter-agent communication is really needed or not. Anyways, it depends upon the application and what is available, whether local sensing is available or not, and so on and so forth. So let me summarize now. We have already shown that swarm aggregation without inter-agent communication, which gives a lot of potential in the cases where there is a hacking kind of possibilities. They're only sensing their position and so on. Can we look forward for and giving the final target? So can we give the local kind? We observe the local behavior, and based on that, where the local behavior is moving, and let's make the decisions based on that. And that's what we would be looking forward. And of course, this could be one kind of extensions people can look at. These are the acknowledgements as well as the articles that can be referred. By the way, this particular work was wonderfully done by an undergrad, Dhruv. He's with Stanford as of now. Vikrant, Shantanu, and Professor Abhishek was also part of this. Thank you. I'm open for questions now.
Thank you, Professor Leena. I think that was a really very interesting talk. And I think there'll certainly be a lot of use cases, I think, as you said, where, communication might not be available, or maybe you don't want to do it for some of the reasons you mentioned. There is one question from the audience. Let me read that out from Amritesh Maitra. Essentially, the Amritesh is asking that in the video which you showed, where the agents are moving towards a goal circle, there doesn't seem to be any other reference agent. So the question is, how are they how is it related to the goal circle? Is there somehow the theta dot which you mentioned, how is that being calculated, or what
Sure. Yeah. So basically here, we tried to solve this problem when the target position is known to us, right? So in a way where you have, for example, the target location is known. That is what is the problem statement is saying. So when you are looking forward for finding this particular theta dot, so basically you know your orientation and where you have to turn towards. All right. So that is what is getting captured through this theta dot, right? And since this is steering control, this is a control law that says that, okay, you move left or right. That's it. Okay, so when you are turning left, you are basically trying to, if you are in a region where you are turning towards the left side, is making sure that you are moving towards the target. That's all is required here. So that's why theta dot is turning out in this. So the differentiation of an angle. Okay, of course, I did not point out this. The differentiation calculations in embedded itself is another problem, because whenever there is a differentiation comes in, the signal is to be really noise free. Any noises cannot be filtered through differentiation. So what we applied here is another signal processing, which is very friendly with embedded processing, right? So because we are only interested in sign of this theta dot.
Correct.
So that solved our problem, kind of.
Actually, there are also some sensors which could be considered, like passive infrared sensors, which directly give you
Yes,
change and rate of change and things like that, which would also reduce your hardware requirement.
Wonderful.
Just one or
Very
two
nice.
more questions I'll ask from again the audience, and maybe in the interest of time, I'll limit it to one question because we'll have the next session starting very soon. So one of the questions from Akshata is, what is the law for interacting with obstacles and walls in the video?
Well, see, we are only looking forward for avoiding collision with whichever comes in the way, whether it is agent or any other obstacle, right? So as soon as a wall comes in, or the obstacle that we showed, what you are looking at is this particular direction. You may change the course of change is what you change the direction again. Again, you are looking at this particular angle. This particular angle is to be the sign of this particular change is what is to be considered here, right? So you make a change in the direction. Now, the next moment you sense is some other direction. So as long as you are bringing this particular field of view and you are weighing that where your target is and what the collision part is, the combination of this is making you to move away from the obstacle, but at the same time finding its own path as and when the path is clear.
Okay, thanks.
So the combination of this control law is making that particular. So we don't categorize whether it is a static obstacle or moving obstacle or anything. This control law is just okay to take it forward.
Thank you very much, Professor Leena. I think that was a really interesting talk. And I apologize to there are 3-4 questions still, but we need to give a short break, a bio break, so that people can come back in time for the next session. But Professor Leena, if possible, you could, if you have access to the chat, maybe you could have a look at the questions, and if possible, maybe answer them in the chat.
Sure.
Okay,
so through the chat window itself, so that
chat window itself. Yeah, you can just
those who want to go for bio break can go.
Yes.
Can take a break, right?
Yeah.
All right.
We will have the next.
I'll be on chat then.
Yes.
All right. Great.
Okay. Thank you.
Thanks.
And
thank you very much.
We'll close this session now, and we'll have the next session start in 3 minutes. So I'll request everyone to come back in time.